Welcome to Insult My Intelligence. Today the topic is Planet 9. Now the way we select our topics is this. Johnny suggests ideas until he finds an area where my ignorance is boundless. This doesn't usually take very long. He says a thing, I say, what are you talking about? And we're off. But when he said, do you know anything about Planet 9? I'm afraid I said, yeah, Pluto is Planet 9. In an episode of QI, this would have been the moment when that giant klaxon goes off. Because, as everybody knows, Pluto isn't the 9th planet anymore. It got downgraded some time ago. Pluto is the X-Planet 9. Despite no longer being a planet, Pluto could still be described as a planetary prediction success story, given the number of planets astronomers have predicted that never materialized. As our first guest, the originator of the current Planet 9 theory, Konstantin Batygin, explained.
Yeah, I think it might be something like the 247th one past 1846. The first kind of credit must be given to Leverrier and Adams for mathematically predicting the existence of the planet Neptune and then actually succeeding.
In the early 19th century, astronomers realized an unexplained force was perturbing the orbit of Uranus and calculated that it must be another unknown planet. In 1846, Neptune was discovered right where its predictors said it would be. In the early 20th century, the astronomer Professor Lawler made similar predictions based on the idea that Neptune alone couldn't account for the perturbations to Uranus, launching a search for what he called Planet X, a search that eventually led to the discovery of Pluto. However, there was a problem. Lowell had predicted something about 7 times the mass of Earth. Pluto is actually 1/500th the mass of Earth. It wasn't until 1992 that we found out there was no Planet X. The calculations that gave rise to the prediction were based on a mistake. Everyone had the mass of Neptune wrong. As Konstantin Batygin puts it,
that planet, that gravitational pull that Lowell and company were chasing down was really there. That the anomaly was there. It's just that the planet was effectively contained inside of Neptune. When Pluto was discovered, it was immediately clear that this thing is kind of small, right? It's a 7th Earth mass object. You should have been able to resolve. And instead, they kind of looked at it and said, well, there's a point. They said, well, maybe it's 1 Earth mass. So Pluto's mass got resolved, sort of downgraded to 1. And then if you make a plot of sort of how the estimate of Pluto's mass evolved since 1930, it just kind of kept going down and down and down. And this is because it's difficult to know how massive something is just by looking at it. You need to detect a satellite and resolve the motion of a satellite around a planet. And that came in 1978 when they're like, oh, shoot, Pluto's tiny.
So there was no way Pluto had enough mass to account for the perturbations to Uranus, which in any case were more than accounted for by the new correct mass of Neptune. And if you're wondering how I can keep saying the phrase perturbations of Uranus with a straight face, it's just practice. This is like my 7th go at this voiceover. But if Pluto isn't a planet, what is it? Here's Professor of Astronomy at the University of Regina, Samantha Lawler, explaining.
So Pluto is the very first Kuiper Belt object that was discovered, right? So the Kuiper Belt, it's kind of like the asteroid belt, but beyond the orbit of Neptune, right? So there's all of these small icy bodies that are orbiting around. And Pluto was the very first one to be discovered, and it's one of the largest ones, but it's not the largest one. So Professor Mike Brown at Caltech discovered Eris in 2005, I think. And that sort of set off this crisis of, oh no, this one's bigger than Pluto. Should this one also be a planet, or should Pluto really not be a planet? Because at that point, we knew about hundreds of Kuiper Belt objects that are on similar orbits to Pluto, but aren't quite as big as Pluto, right? So at the time, I was actually taking a class from Mike Brown at Caltech. I was an undergrad there. So it was pretty neat to see this all play out in kind of real time. And then the International Astronomical Union sat down and actually wrote a definition for what is a planet, and Pluto got kicked out, got demoted, right? And so now it's what's called a dwarf planet. It's large enough to pull itself into a round shape, but it's not large enough to clear its orbit of similarly sized objects.
So what does this have to do with today's topic, Planet 9? Well, two astrophysicists, Mike Brown and Konstantin Batygin of Caltech, noticed that a small group of these very distant Kuiper Belt objects were all clustered together in the night sky. These objects are so far past Neptune that they had escaped its gravitational influence, but something big had to be shepherding these planets into these clustered orbits. Their theory was that a ninth planet, one about 5 times the size of Earth, which so far nobody has seen because it's really far away, was responsible. So if Pluto is now the X Planet 9, Planet 9 may be the new Planet X. And even though we can't see it, Konstantin Batygin is now 99.8% certain that it's out there. Here he is explaining more.
Of course, the notion that the solar system can host another planet is not a new one, as we just discussed. But this particular formulation of the Planet 9 hypothesis really traces its origins maybe back to 2015, 2014 or so. And my partner in crime on this, Mike Brown, and I were inspired by work that some other astronomers had done, Chad Trujillo and Scott Shepard. What they had done is they had discovered a second object in the solar system, which had an orbit, didn't interact with Neptune. You see, beyond Neptune, there's this field of debris, and if you kind of ask all this field of debris that we conventionally call the Kuiper Belt, how are you doing? The answer will be we're doing not so great because we're being kicked around by Neptune every orbit, right? And the orbits are kind of chaotically diffusing and being tossed around. Now, a few of the objects, if you go distant enough, actually aren't part of this, chaotic group. These are objects that the first of these is Sedna. It was discovered, in fact, by Mike back in 2003. And then the second bona fide detached object, which was nicknamed Joe Biden, was discovered back in 2013 or 14.
It was actually discovered in 2012. And by the way, it's not nicknamed Joe Biden because it's a detached object. It's just that its real name is 2012 VP113, and Joe Biden was the VP in 2012.
We were inspired by their work because their work had pointed out that the argument of perihelion, which is a strange thing, the argument of perihelion is an angle made by an orbit between the point where it crosses the plane of the Earth and the closest approach to the Sun. Okay, it's kind of an obscure thing.
When he said this, I nodded along, but I didn't know what the argument of perihelion meant. After Googling it, I still don't really understand, but it's basically the angle of a celestial body, in this case these Kuiper Belt objects, when they cross the plane of the Sun at their closest point. Anyway, this number is used by Brown and Batygin to show the similarities in the orbits of these extreme KBOs.
Right? It's not this obscure representation of some angle. It's just a consequence of the fact that the orbits are all pointing in the same direction. They all kind of are tilted into the same plane. Even back then, we just intuitively recognized that this pattern of clustering could not apply uniformly to the stable and unstable population of the Kuiper Belt objects. The ones that are being punched around by Neptune, right, are just cannot possibly exhibit this pattern. Even though back then, the two objects that were in this unstable category kind of looked like they fit. And indeed, this is after running the mathematical models, we made effectively this. I wouldn't call it a prediction, but the statement on which the whole thing hinges, which is that as more objects are collected, the dynamically stable, the things that are not being kicked around by Neptune very strongly, will continue to exhibit, on average, clustering.
Right. So these are far away Kuiper Belt objects.
Right.
Which is how, I guess you measure these things in astronomical units, which is the distance between the Sun and the Earth.
That's right. Yeah. So the way to think about it is these are things because that's not a particularly intuitive It's not an intuitive unit of length, but the orbital period is a more intuitive one. So it takes these things more than 4,000 years to go around the sun. Right? That's where the boundary for everything we are talking about starts. Right? If you're orbiting beyond that critical orbital period, then you're part of the Planet Nine Club potentially.
Your hypothesis was that the most likely mathematical explanation for their clustering was there was a big planet that we couldn't see out there influencing their orbit. Is that
Right, right. I mean, really, all I want to be like, completely kind of honest about this. All that I can do with the calculations that we run is predict an orbit and a mass of something. So I can't tell you if it's a 5 Earth mass burrito. Maybe it's a 5 Earth mass. I don't know,
that would be
beer
good?
beer glass. I don't know. Like it could be anything. It could be as long as it's 5 Earth masses, it can really be anything. But then you come to the question of what things come in 5 Earth mass. What things in the universe get stamped out at 5 Earth masses, and the typical thing is planets. So that's kind of where the planet assumption comes from. We think Planet Nine is the most reasonable of the explanation, but really what we're seeing is just some one-way gravitational sign towards some external potential, some external gravitational force that's confining these distant Kuiper belt objects.
And its orbit is a bit strange. It's on a different plane than the planets that we can see, and it's. Will you explain?
Yeah, look, so it's completely unlike what you would imagine the solar system to be like, in sort of a mobile that you hang up over a kid's crib. Um, yeah, this orbit is first of all appreciably eccentric, and it's out of round by about 30-40%, something like that. It is tilted by about 20 degrees with respect to the plane of the solar system, and it's really far away. I mean, Planet Nine takes something like 10,000 years to go around the sun. Now, all of these things immediately point to the fact that it's very unlikely that it formed in place. It's probably a consequence of formation, really a formation of Uranus and Neptune, because Uranus and Neptune itself were possibly assembled from sort of 5 Earth mass building blocks, and that accretion process is never 100% efficient. You end up scattering some of these building blocks out of the solar system, largely because Jupiter and Saturn are so massive. And early in the solar system, there exists a process by which some of these objects that are being scattered out can get trapped at large orbital periods. So we think one plausible hypothesis for how Planet Nine got there, acquired its strange orbit, is that it was another growing ice giant in the primordial solar system that sort of got evicted from the party, if you will, and then is just kind of lurking around.
So the 99.8% probability that Batygin and Brown often cite, where does this come from?
It comes from a calculation of how certain are we that the clustering that we see in the night sky, right, this clustering of distant orbits that we see, is actually there. There's a 0.2% chance, given the data set as of 2019, that this is all a fluke. This is all a fluke and a pipe dream. So, that's not a high probability, obviously, but it is nevertheless a material chance.
In a minute, we'll talk to Samantha Lawler, Professor of Astronomy at the University of Regina in Saskatchewan, about why she is skeptical about Planet Nine's existence. So, Planet Nine, what is its alleged existence meant to account for?
Yeah, the very most distant Kuiper belt objects are really hard to find, right? So we are extremely biased toward finding the very closest Kuiper belt objects. So they don't make their own light, right? They're not like stars. So we see them in reflected light, which means light from the sun has to go all the way out to the Kuiper Belt object and reflect all the way back to Earth, which is almost the same distance as the sun from these very distant objects, right? So the brightness drops off as 1 over distance to the 4th power, right? So as you go further away, if you have a Kuiper Belt object that's 10 times farther away, it's going to be 10,000 times fainter than one that's 10 times closer, right? So you're very biased toward finding the closest ones. So we've only found a handful of really distant ones. And the first few that were discovered were all kind of clustered in the same direction, right? They're all kind of pointed toward the same part of the solar system. They had their closest, they're on very eccentric orbits, which means, long squished orbits, right? So they have one part of their orbit is very close to the sun and one part of their orbit is very far away from the sun. And we can only see them when they're at their closest point. And these first few that were discovered were all pointed in the same direction, right? They had their most distant, the distant part of their orbits was was all on the same side of the solar system.
Right.
And so that's where the Planet 9 theory came in, is that if you have a really distant, very large planet out there, it could be sort of confining all of these really distant orbits to be off on the same side of the solar system.
So it's
that's
tugging them
where
in.
the theory came from.
It's tugging them in that direction, basically.
Yeah, it sort of gives them a gravitational kick at the right time in its orbit to keep them all over there, right? It's
clustered.
It's a very complicated dynamical process. Like Mike Brown and Konstantin Batygin are very good at orbital dynamics. So it's a really good theory.
So Mike Brown, who you studied with, he's one of the two guys who came up with this. What is it about your old mentor's theory that you think doesn't work?
Yeah, so the part that's tricky is so these are really hard to find, right? Which means that you're very biased toward finding them only where you look on the sky, right? And so these very first ones that were discovered, we didn't know if they were all kind of discovered in the same part of the sky, right? Because their most distant the distant parts of their orbits are all pointed in the same direction. That means that the closest parts of their orbit are kind of in the same direction on the sky, right? So does that mean that all of those are actually on that side of the solar system, or does that mean that we didn't look in the other direction, right? Astronomers, and I think most scientists, you don't like reporting like, oh yeah, I looked at all of this part of the sky and I didn't find what I was looking for, right? Like that's not something that you really report, right? Like there's databases of discovered Kuiper Belt objects, but there's not databases of where you looked and didn't find anything. But that's actually really important information, right? So that's something that we tried to be very careful about in the Outer Solar System's Origin Survey, which I was part of, where we really carefully kept track of exactly where we looked on the sky and reported all of that information so that other people can take our discoveries and understand what biases went into those discoveries, right? So as more and more of these very distant Kuiper Belt objects have been discovered, they're not quite as strongly clustered anymore. There's a little bit more spread in their clustering, and there's a couple that are in the opposite direction now. And so all of these discoveries are made with ground-based telescopes, which means that we're subject to weather, right? So I'm part of another collaboration where we're trying to discover more distant Kuiper Belt objects, right? And we just tried to look in January, right? January is the worst weather. So that means that the Kuiper Belt objects that are easiest to find in January, we can't find them because the weather's always bad on Mauna Kea in January, right? So that's a bias, right? We're not going to find Kuiper Belt objects in that direction just because of the weather.
You were just talking about the Outer Solar System Origin Survey. What exactly did you? Because this is like a 40 astronomer
Yeah,
thing, isn't it? And you set out to just look for stuff. I mean, to look
yeah.
for
So
Kuiper Belt objects, basically.
yeah. So just try to find as many Kuiper Belt objects as possible, and track them all carefully, and understand all of our biases, right? So we managed to discover more than 800 new ones, which is a lot for how many are known, right? So you have to keep following the Kuiper Belt objects for a number of years in order to get good measurements of their orbits. Um, so we very carefully did that. We weren't biased toward finding certain types of orbits, and so you're able to take our discoveries and say, okay, if the orbital distribution of the Kuiper Belt looked like this, what would you have discovered? And we have some software you can use to test different models and compare it with our discoveries, right? So it's a way of taking out the biases in your survey, which other surveys had not done before. Now other surveys have done it too, so there's other discoveries from. It's called the Dark Energy Survey. They also had a lot of Kuiper Belt objects they discovered, and they also tried to take the biases out of their survey. They also did not see any evidence for clustering.
And
So,
these of in your survey, did you discover extreme Kuiper Belt objects, or there's another word, sort of high perihelion?
Yeah, so
object?
Perihelion being the closest point in the orbit to the sun. These are the ones that never get very close to the sun, the ones that are supposed to be clustered, right? So we discovered 4 of them, right? So that doesn't sound like very many, but the original theory came from only 6.
Right.
6 Kuiper Belt objects that were clustered. So we discovered 4 more. And there's no evidence for clustering in those 4, right? So you might say, okay, well, that's not very many. So the Dark Energy Survey also discovered another 4, and there was also no evidence for clustering in those 4. And then there was recently a paper that came out led by Kevin Napier at University of Michigan. He's a PhD student there, and they took so his team took our survey, the Dark Energy Survey, and a survey by Scott Shepard and Chad Trujillo, and put them all together to try to take the biases out of all those surveys and add together all of the discoveries. And they also found no evidence for clustering.
This study that came from Kevin Napier has been a big point of Planet 9 debate since it was released earlier this year. Looking at all the recently discovered distant Kuiper Belt objects, the study concludes that in the areas looked at, there is evidence for a more uniform distribution of the KBOs. This undermines the Planet 9 theory in that it alleges that the clustering observed by Batygin and Brown is actually just the distribution we would see across the solar system. But Batygin claims you can't draw these conclusions from the study as the rest of the solar system still hasn't been checked, and the area being looked at is still very similar to the area observed back in 2016 when the theory first came about.
Well, it's really, it comes down to, statistics. There being 2 ways to do the statistics. Number one, the kind of way that if you have this distant census of Kuiper Belt objects, you can take a small subset of them for which you know very well how they were discovered, and pointing history of telescopes. All of this is very well characterized, and you say, and you ask, well, given the fact that given this pointing history, would we have the statistical question that they ask and then answer is, do these objects, were they discovered only in high probability regions of where we looked? Meaning, did we find Kuiper Belt objects where we looked? And the answer, unanimously, absolutely yes, right? So from there, right, you take a bit of a logical jump and you say, well, if you find Kuiper Belt objects where you look with the telescope, that must mean they're everywhere. Okay, that logical jump doesn't actually follow, especially for these surveys like the DES, which has contributed quite a bit quite a few objects because they actually look directly at the cluster. The other approach to do this, which I think is the better, kind of more informative approach, is to forget about who discovered what on the night sky, and just say, okay, you have a census of thousands of discoveries, thousands of Kuiper Belt objects, and if there's one, I don't know, over there, and it has a given brightness, that means that somebody looked over there and was able to discover an object of at least that brightness. So-called observability mapping approach allows you to get and kind of use the power of the comparison sample of Kuiper Belt objects being large to inform better the question of what is the likelihood that the collective observational effort of the night sky would have discovered the cluster, the uniform distribution, had it been there. And the answer is 0.2%, right? The 0.2%. So it's really, remember, right? There's lies, damn lies, and statistics, and you can do your statistics in different ways. I'm not saying that my colleagues did anything wrong. The exercise they did is 100% correct. It's just that the question that they're asking and answering is one that's somewhat distinct from are the objects clustered or not. It's did we discover them only where we looked? And the answer is yes. Yeah, it would have been profound, by the way, if the answer was no. I mean, this is not a joke. Like, if the answer is you have a huge region and you only find things at like the edge of where you look, then you immediately know that something interesting is going on. But if you have a tiny, or not a tiny, but like a limited region of the sky, and you only find them where you see, it's not really conclusive.
Right. And I guess the problem is we're not talking about that many Kuiper Belt objects. That's
right. Yeah, there's the full census is about 20, and if you limit yourself down to only the really well characterized ones, it's 14, and to get to 14, you actually kind of have to stretch how you count them, right? You have to include the objects that have orbital periods somewhat less than 4,000 years. So you really cut your data set basically in half when you go to this. And further down, if you exclude the dynamically unstable objects that are never supposed to cluster in the first place. This is a subtle point that often gets missed, is that asking whether the full data set is clustered is interesting, but it misses a key element, which is that things that hug the orbit of Neptune and are being punched around gravitationally by Neptune will not cluster even if Planet 9 is there. It's only the detached objects, the things that are dynamically stable, that should exhibit these patterns. And of the 11 objects that are stable, 10 cluster beautifully, and 1 is anti-aligned. So that's how we back in 2016, we went from 4 alignment being 4 out of 4. Now the alignment is 10 out of 11.
But Samantha Lawler is not convinced by these explanations.
You can't. It's one of those things where you can't say that it doesn't exist, right? You can't say that there's no way to prove that Planet 9 doesn't exist, but we can say that there's no evidence for the piece of evidence that suggested Planet 9 exists, right?
Is that the same thing as saying that we don't need to find an explanation that we don't understand yet for the data we have? I mean, is it explained by the gravitational arrangements that we know about already, or do we need some kind of explanation?
Yeah, so out of all of these high paracenter or high perihelion Kuiper Belt objects, the ones that never get very close in, we can explain the orbits of all of them with known dynamics, known gravitational interactions, either with the solar system or with the galaxy, except for 2. There's 2 that we cannot explain with what we know about the solar system, and that's Sedna and VP113, these very distant ones.
So you're saying that we do need some kind of
Yes, so
theory
we do need
to account for those.
something to explain those two, right? So there's a whole bunch of theories that have been suggested, right? And Planet Nine is one of those possible theories. So some of the possible theories, I'm actually going to look at my list here. So that, there could have been a rogue planet in the outer solar system. In the early days of the solar system, there was maybe a fifth planet or a fifth giant planet out there that got ejected from the solar system. That's one way to explain it. It could have possibly been captured from another solar system, right? These really high paracenter objects. It could have been a star flew past way back in the early days of the solar system. It could have just been gravitational perturbations from all of the gas that was around when the sun formed. And it could be just dynamics that we don't fully explain from the Oort cloud, right? So there's a lot of possible explanations, and Planet Nine is one of those possible explanations.
It might seem weird to think that there's a planet 5 times the mass of Earth in our solar system that we never knew about and still can't see. But it's not weird to have a 5 Earth mass planet in general. It's a very common size for a planet in other star systems we know about. In fact, it's the most common size, so it's actually sort of weird that we don't have one, unless we do. What happens next with Planet 9 will almost certainly be thanks to a massive new telescope that's about to come online. The Vera C. Rubin Observatory in Chile has a primary mirror the width of a tennis court, and it's about to embark on what's called the Legacy Survey of Space and Time, a 10-year project.
I expect that we will have found it within this decade, for sure. My certainty is not one that comes from some religious obsession with Planet Nine. It really comes from the fact that I know that the mathematical models are right, and the data appears to be stacking up pretty well. So when I'm merely following the kind of the track laid out by mathematical reasoning. At some point, if the whole thing breaks down, I will gladly announce that the whole thing was just a red herring. But it's important to chase these things down.
How long will it take not to find? I mean, how long would it be before you could rule it out?
Similar timescale, because we now with the Vera Rubin Observatory coming online within the next couple of years, the census of Kuiper Belt objects will go up by hopefully a factor of 10, right? And so we will be able to say with significant certainty whether these patterns are there really, right? Like with better certainty than 0.1% that we keep referring to. And I think that's going to kind of be the final kind of stamp on all this. My sense is that Vera Rubin will just discover Planet Nine, and that'll be the end of this story.
How will you sort of personally feel if in the next couple of years they find Planet Nine?
Oh, I would be delighted if they found Planet Nine. That would be so cool. I mean, there's exoplanet systems that we know of, planets around other stars that have really distant planets on orbits like that, right? But we don't know anything about what the inner parts of those planetary systems are like, right? So they could have, an entire solar system like we have and something really far away, or maybe those are two totally different types of systems, right? We don't know yet. So that would be a really cool piece of evidence just for, how does our solar system fit in with other solar systems that we've discovered? So I would be completely delighted to be wrong and for Planet Nine to be real. That would be absolutely fascinating. But right now, I don't think the evidence is there.
Because I guess a 5 to 10 times the mass of Earth planet is the one thing our set is missing, isn't it? I mean, lots of solar systems have them and we don't.
Yeah, exactly, right? Like the most common size of exoplanet is something that we do not have in our solar system. And we don't know, would that be a water planet? Would it be a planet with a really thick atmosphere? Would it, be something halfway in between the Earth and Neptune? Or Like we don't know the most common type of planet in the galaxy, and we have no idea what it looks like, right? So it would be really cool to have one in our own solar system to study.
Even after all that, I couldn't possibly make a case myself for or against Planet 9. But at least I now know what it's supposed to be. It seems weird to me that there could be something out there that big and significant in our own solar system that we can't see and aren't sure about. But hopefully we can find it within the next few years, and then we'll finally have a replacement for Pluto. Maybe we could just call it Pluto.
David Bowie is another one that came up. We were immediately opposed to giving it some godly name, just because I feel like before you have confirmed it, that's not the right call. Also, there are no good, Greco-Roman gods left, because they've all been used up for asteroids. I think that the demigod of like untied shoelaces might still be available, but it's slim pickings out there.
Thanks for listening to this episode of Insult My Intelligence, and thank you to my guests, Professors Samantha Lawler and Konstantin Batygin. Next week, we'll be discussing left-handedness, why some of us have this difference, and what advantages and or disadvantages it can bring. And a bit of a spoiler alert, one of the reasons I'm interested is because I am, myself, left-handed. The astronomer Percival Lowell made similar predictions based on the idea that Neptune alone couldn't account for the perturbations to your... Go again. Just go again.